Hello everyone and welcome to this lecture about free vibrations in strings, where I will do an example for free vibrations to apply the general theory that we derived in the previous lecture. I've stated again the equation of motion and the boundary conditions, and now I will look at a specific case where this string is basically plugged in the middle at x is L over 2, such that the initial shape becomes more or less triangular, like this. Okay. The height here, let me call that h, and basically the string is released from this configuration at rest. Okay, so the initial conditions can be written as follows. The initial shape v of x at time 0 that we called v0 of x can basically be split into two parts. For the section that in between 0 and L over 2, the function can be written as 2hx divided by L. And for the section between L over 2 and L, it can be written as 2h minus 2hx divided by L. So this holds from 0 to L over 2, and this holds from L over 2 to L. Okay, and the initial velocity is equal to this v0 x, but we will assume that it is 0 in this case. Okay, so we plug the string in the middle, release it, and we are wondering what is the response of the system as a function of time. Okay, for that we are going to need again the expression for the natural frequencies and modes. So let me write these down again. We found that the natural frequencies are n pi times the square root of t divided by rho a L squared. The modes Vn are alpha times the sine of n pi x divided by L, where n runs from 1 all the way to infinity, and we mass normalize the modes such that alpha is 2 divided by rho a L. Okay, very well. What we also need is this concept of modal expansion. So in the end we are going to write the displacement field V as a function of x and t as an infinite sum. Let me use n now. N is 1 to infinity of Vn, which is a function of x, times eta n, which is a function of t, where eta n is solved from the modal equations, and we have seen in the previous lecture that this is just the initial value times the cosine of omega nt plus the initial velocity divided by the corresponding natural frequency times the sine of omega nt. Okay, now, and this second term, because the initial velocity is 0, that one will be 0 as well. So it's in fact only cosines in time. Now the question is, how do we end up with this expression for eta n at 0? Well, for that, I need to recall that we had to solve this integral, right? Let me first write it down in this general form. We had that eta n at 0 was rho a times the integral from 0 to L of Vn times V0 dx. So this is the integral that we need to solve. Okay, let's substitute then this initial shape into this expression. And we need to split this integral now in an integral from 0 to L over 2 and an integral from L over 2 to L. So this can be written as, well, let me do it like this. Rho a times the integral from 0 to L over 2 times 2hx divided by L times alpha sine of n pi x divided by L dx, okay, plus rho a times the integral of L over 2 to L of 2h minus 2h x divided by L times alpha sine n pi x divided by L dx. So we have these two integrals. Now, carrying out these integrals, doing the integration, that is actually quite a bit of work, because we have the general form of these expressions are x times the sine of something with x. For that we need integration by parts. So in order to really do this, this is a lot of additional work. However, you will see that a lot of terms, once we substitute the integration boundaries, will actually vanish. So I'm going to skip a lot of terms, a lot of writing, okay? And I will just show you the result, because I think it will take quite some time to actually do this. Yeah, and that's a bit of a waste in this lecture. So the result can be written as 4 rho a times L h alpha divided by n squared pi squared, okay, times the sine of n pi divided by 2. So I would recommend you to try and see if you can come up with this same expression, okay? And this is then for n is 1 all the way to infinity. Now, let's have a look at this expression. What you see here is that for n is 1, the sine of pi over 2 is just is 1. So we have some positive contribution there. Then for n is 2, we actually have the sine of pi, which is 0. And if we continue like this, we will see that for n is 3, there will be a negative contribution. For n is 4, it's 0 again. So in fact, only the odd numbered modes, so 1, 3, 5, and so on, will have a non-zero contribution. All the even modes, 2, 4, 6, are all 0. And that the non-zero modes alternate between positive and negative contributions. Okay, so yeah, maybe it's nice if I write down that, so for example, that n1 at 0 is 4 rho a l h alpha divided by pi squared. All right, and n eta 2 at 0 is 0, eta 3 at 0 is then minus 4 rho a l h alpha divided by 9 pi squared, and so on. Okay, now what you can see, maybe if we go back to the original problem, you can see that this initial excitation is symmetric about L over 2. And all these even modes, so 2, 4, 6, are anti-symmetric about that point. Whereas all the odd modes are symmetric as well. So what you see is that because the initial shape is symmetric, it basically only excites also symmetric modes. So that is the reason why all the even mode shapes are not in the response. They are not excited. Okay, so with this we have the solution for eta n at 0, okay, that we can now back substitute into the solution for eta n as a function of time. So eta n as a function of time is this 4 rho a l h alpha divided by n squared pi squared times the sine of n pi over 2 times the cosine of omega n t. All right. And then finally, by back substitution into the modal expansion, over here it is, we need to multiply this by the mode shape Vn and sum. Okay, so this will then be, let me try to put this in the same screen. Yeah, so we have V as a function of x and t will be the infinite sum, n is 1 to infinity, of for rho a l h, and now it becomes alpha squared because in Vn is still an alpha, divided by n squared pi squared times the sine of n pi divided by 2. The mode shapes were all sines, so we have sines n pi x divided by L, and then the behavior in time is harmonic with omega nt, like this. Now, alpha squared was determined. It was, the alpha was the square root of 2 over rho al, so alpha squared is the same without the square root. So that simplifies the solution a little bit. So the total solution, let me write it down here on a separate line, is the infinite sum, n is 1 to infinity, of 8h divided by n squared pi squared times the sine of n pi over 2 times the sine of n pi x over L times the cosine of omega nt. So this is the final solution, the total solution for free vibrations of this example. Now I want to emphasize a couple of things. Solution for free vibrations. Free vibrations. I want to highlight a couple of things. First of all, we see this term cosine omega nt here. This is the behavior in time. So we see that the response is harmonic in time. This function here, the sine that still has an argument with x, shows the shape of the string. So these are the modes. These are all sines. And then we have this term in front that basically is what we call a modal participation. Modal participation factor that specifies how much each of these modes is actually in the solution. So we see that for starters, only the odd numbered modes do participate in the solution. And we see from this ratio in front of the sign, the fact that this n squared is in the denominator, that the participation of higher modes decreases very rapidly with the modal number n. So what you can see here is that for n is 1, the denominator is 1. For n is 3, it's already a factor 9. Maybe if I continue here, let me also write down n5 at 0. That is 4 rho a l h alpha, already divided by a factor of 25 pi squared. So you can see that the importance, the relative importance of higher modes very rapidly goes down. And that is why in practice, only a finite number of mode shapes is sufficient to describe what is going on. So in theory, in general, we have this infinite sum, but in practice, it is sufficient to approximate the behavior by only a finite number of natural modes. Okay, so I hope this clarifies a little bit the general procedure that I discussed in the last lecture. You will see that for these free vibration response, the majority of the work is actually in computing the initial values for the modal coordinates. But once we have established these, determining the total response is actually quite straightforward. All right, so I hope this helped you out a bit. Thanks for watching. See you in the next lecture.